The purpose of this video is to show the development of triangular neighborhood networks from the smallest networks to what could be considered to be intermediate sized networks. So if you have the question, how do I build a universe? You could start with one node. The only sort of thing you can do with that node is to send signals back to itself. That's really not very interesting, okay? If, on the other hand, you have two nodes like this, then you can send a signal in this direction, or you can send a signal in that direction. And that's interesting, but so what? Okay, one could say. If, on the other hand, you have two nodes, or three nodes, two edges, then you could send a signal to here, and then once the signal got here, it could be sent to here, and once it got here, it could be sent back again, and then once it got here, it could be sent back again like this. But this is basically all you can do with this sort of a network. It's interesting, but then not really. On the other hand, if you had three nodes and three edges, so that each node had two edges connected to it in a triangle, now you can send signals here, here, and here, and then or the reverse, like this. And that's interesting, but not really. But this is the first instance of a triangular neighborhood network, in the sense that the three nodes, each connected to each other, form a triangle. And so this is the basic building block for the triangular neighborhood networks that I'll be showing you in the videos that I've made. Now, once we have three nodes forming a triangle like this, we could add a fourth node, again with three edges. And now we have a much more complicated three-dimensional network. In this network, each of the nodes has three edges coming into it, and together they form four triangular neighborhoods like this, and this is much more interesting. Now, of course, in this network, I'll erase this and redraw it again so you can see it a bit more clearly. Like this. Now, in this sort of a network, you can send a signal here, and then when it comes to this node, the question is, does it go down here or does it go down here? And I'll show you transform tables in the next video or so that says, will tell you what happens. Well, let's, for the moment, assume that the signal goes here, and when it arrives at this node, once again, the question is, where does the signal go? Does it go back? Does it go to the left? Does it go to the right? Let's say it goes this way. And now when the signal arrives here, the question again is repeated. There's a transform of a signal pattern entering and a signal pattern leaving the node at a given time. And so let's say it goes like this. And then when the signal comes over here, the question again is, where does it go? And it can go as it did here, or it can go this way, for example. So there's a much more complicated pattern of signal movement and signal interactions. For example, I'll redraw this once again. This goes over and over again, redrawing. So supposing you have a signal coming in here and a signal coming in here. And now you have the question really of what are you going to do? Does this signal go like this? And what do you do with that signal? Does it go like this? Or does it go itself like this? Or does it go back again like that? So there's a whole bunch of questions as to when you have more than one signal approaching a node, as to how the signals interact with each other, and what's the resulting outflow of the signals from the node. And we'll discuss that in great detail in videos to come. So now we can discuss the same questions once again, only using the Knupfli elements as the representational medium. Here we have once again one edge as one plastic Knupfli element. And again, we could discuss the question of how signals flow in this one edge. As we did before, we can make a network of just two edges and discuss what happens to the signals in that network. And here's a grouping of three edges forming three nodes, each of which have two edges coming to the node. And as before, we can add three edges forming one three-edge node, and we can attach this to this network here, to this network. And I'll do this by hand. You see how long it takes to do this each time, and this is the only time, in a certain sense, ever that I'll show you how I do this, and in a certain sense how quickly one can change the topology of a network. So now we have a three-dimensional object that consists of four three-edge nodes connected by six edges. Now in this case, some of the edges are light blue and others are pink. But we can recolor the object like this, and these are the same objects, I mean topologically, so it's just the coloring has changed. And so in the same way that we had this network here, we can choose one particular triangle here and add three more edges. Now I'll explain later in one of the later videos why adding three edges at a time is important and how this is done and the significance of this. But for the moment, let's just consider the act of adding three edges at a time. You really can't add one edge, you really can't add two edges, but in this triangular neighborhood syntax, you can add three edges. That's what I'm doing. So here again, we've chosen a particular face, we've added three edges, and now this is the resulting object. And of course, as before, we can recolor the object, and so what you see now is that this object has five nodes. Three of them are four-edge nodes, and two of them are three-edge nodes, here and here. So just by adding three edges to the structure, we've changed it from being all three-edge nodes to having some of the nodes be three-edge and some of the nodes being four-edge. And this, as we add three edges at a time, we'll see that this happens in various places and various occasions. So let's take this object here once again and add three edges to it. Now you see this had three four-edge nodes and two three-edge nodes, and now when we added three more edges, we have two five-edge nodes here and here, and two three-edge nodes and two four-edge nodes. So the topological complexity of this object is much greater. And so we can, as usual, recolor these objects. I mean, they're the same topological objects. And you see now that this is much more interesting. So let's take this structure once again and color it so that this edge is highlighted. And now we're going to do a transformation of this structure by edge rotation. We're going to take this edge and move it into these nodes. So once again, I'm going to do this in front of the camera, because I want you to see that it's really real, and the transformation is obvious. So when I rotate this one edge, we're going to transform the structure from one that had two 5-edge nodes, two 4-edge nodes, and two 3-edge nodes into a structure that has only 4-edge nodes. See, the whole structure now has only 4-edge nodes. And this is the first instance of transformation where edge rotation turns one structure into another, or by implication the structure back into this structure here. So again, if we start with this structure here that has two 5-edge nodes, two 4-edge nodes, and two 3-edge nodes, if we recolor it to show the other edges that could be rotated, we see that we have two structures here with opposite edges. Now if we take either one of these and do the edge rotation, and again, once I'll do this by hand only because I want you to see that the edge rotation actually has meaning. If I do this rather complicated process of disconnecting and reconnecting the edges, which I have to do in the physical model, what you see is that the model, which had been opposites, in fact becomes the same. So this model can transform into this, and this model could transform into its opposite. So let me just do that once again to show you this is really true. I know it seems repetitive, but unless you actually see me doing this, you won't believe me. I know that. But once I've done it here in front of the camera, there's no not believing. And so now I've transformed that structure back. So what this shows then is that you can take this structure, do an edge rotation, and you get this structure. And if you take this structure and do an edge rotation, you get this structure. That's interesting. So then there are two other colorations here. Here are two opposing edges. And if you try to rotate this edge here, well then of course you're going to remove an edge from a 3-edge node. And you can't do that because then you'd have a 2-edge node and you have nothing else to connect it to. So neither this transformation nor that transformation is allowed. And in the same sense, there are two other sets of edges in this structure that could be rotated. Once again, this edge here could be rotated, but again, you're removing an edge from a 3-edge node, and so that's prohibited. So these 4 transformations here are disallowed. And these 2 transformations are allowed. And then if you choose this edge here, and then these 2 transform into each other like this. So this is the pattern of transformation, allowed transformations of these this particular structure. And this is very interesting. And we'll see these structures and structures like them of this size and larger over and over and over again. It's really rather amazing that edge rotation is all you really need in a triangular neighborhood network in order to be able to transform one connectivity into another. So let's once again take this model here, only this time we'll color a different edge, this back edge here, and see how the model transforms. So once again, I'll do this by hand, just to convince you that it's real. And so what you see is that these 5-edge nodes have been transformed into 6-edge nodes. And that the structure now looks like this thing. So we started off with this model here, and by rotating the edge here into here, we transformed this structure into this structure. Now these are both triangular neighborhood structures. So this shows you the complete set of, I think, of transformations of this rather simple structure. We'll see in larger structures what happens there. So once again, let's take this little structure here, and remember that we can transform this structure into this structure by just one edge rotation. So now let's take some, since these are all 4-edge nodes, let's just take some random triangle here and add 3 more edges. And so now we get this structure. And if we were to transform this, I'll just, once again, it seems rather boring, I suppose, to watch me do this transformation stuff over and over again. But it really has meaning, at least to me. Hopefully to you too. But now I've transformed the structure once again by edge rotation. And so now we get a structure that looks like this. And that was taking this thing here, adding 3 edges to it, and then doing an edge rotation. So this can go on forever and ever. I mean, and hopefully I won't do that. But so taking this basic structure again, we can just add 3 edges in lots of different places. And then we get crazy structures. And then we can do edge rotations, and they'll chain them into other connectivities. So this is the main point that I want to make at this instance of the video, and that is we can keep adding 3 sets of 3 edges and keep transforming them, and in doing so we can explore all of the configurations of a structure of a given size. And so, I mean, you saw how we started with this structure, and then we transformed its various edges, and now we've added edges to the structure. Since this is equivalent, just a transformation of this, then we can also get that by adding 3 edges and rotating. So it's a rather interesting process that we've gone through. So now if we sort of nilly-willy start adding sets of 3 edges to a given structure, the structure is going to grow. That's pretty clear. So what I'm just going to do is show you a series of additions of 3 edges to some configuration as the sizes get bigger. I think this is bigger, I don't know. But you see that they go on in different ways, and they do different things. Here's a bit larger structure. Okay. Well, at some point, we're going to have a larger structure. And of course, the edge rotations enable the structure to transform itself. And how or why these edge rotations occur, that's the subject of a different video. But at some point, what happens is that the structure gets, by means of edge addition and edge rotation, to be the icosahedron. And the feature of the icosahedron is that all of the nodes have 5 edges coming into them. So having gotten to the icosahedron, which is uniform 5-edged nodes, we can now shift from the loose weave to the tight weave. The tight weave, in this case, the 5-edged node is shown in purple. But once we've done that, we can continue to add sets of edges, 3 edges to the structure. So in going from the icosahedron to this structure here, we add 2 sets of 3-edge nodes, and this produces a sort of a flat structure. If we add 3 more edges to it, we get a structure like this, which is basically triangular in nature. And then, of course, if we add 3 more edges, we get a structure which is basically tetrahedral in nature. And then if we add 3 more edges there, we get a structure which is basically like a tube. And so each of these structures can be built by adding, in this case, to this structure, 2 sets of 3, to this structure, another set of 3, to this, another set of 3 here, and yet another set here. So you see how the shapes and the organizations of the nodes change quite dramatically just by the addition of either 1 or 2 sets of 3-edge nodes. This is the structure with 5 6-edge nodes, and if we add 3 more edges, we get this structure, which is relatively flat. This has 6 6-edge nodes. If we add 3 more edges to this, we get the structure with 7 6-edge nodes, and that has a flat face on one side and a convex face on the other side. And then if we add 3 more edges, we get the structure with 8 6-edge nodes, but it has several variants. This is one. This is basically the 6 pipe. There's 6 6-edge nodes around the periphery, and then 1 6-edge node on either end of the structure. So this structure is the pipe that we'll see much more in the future. We can go on from here up to any size of structure by the addition of 3 edges at a time. Some of them are very symmetric, many of them are asymmetric.